Welcome back to this class. So let's start back with whatever we had been discussing. So yesterday we discussed a lot on the scenario analysis and in general the sensitivity analysis related discussions, and we saw how slight variation in a particular variable could actually cause you to change the decision, right? So yeah, scenarios we were discussing in general, it's a very powerful tool. It can give you idea of what are the sensitive variables and where you should focus more your energy. But without the probability estimation, sometimes it is a difficult to just give a clear answer of which alternative to select, right? We saw some ideas where in certain cases, scenario analysis can immediately result into a clear choice that, okay, this project is better. Absolutely. In all the three worst, best, normal scenarios, it is performing than the other alternative. So it is the best choice. But there could be more complex I would say like the overlapping, and then you need an estimate of the probability part of it. I've also shared one, I think 15 or 17 page document with you in the classroom. That's basically a introduction of your probability and statistics. If any of you does not have any background, or if you just want to refresh your concepts, just go through that document. It's very simple. If you don't understand, again, let me know. I'll help you out to reach those concepts and understand those concepts. Okay. So, essentially, the probability is something that, how do you assimilate the probability based concept in the analysis that we have been doing is what we will be covering in today's class. And in general, the risk analysis is very closely associated with statistics and probability. You will be always be asked, there are n number of risks, political risk, demand risk, blah, blah, blah. How do you assign a probability is the game. Again, as I told, in general, risk is something which you can have a value, which you can assign a chance value. The uncertainty is more or less a challenge, but in this particular course, we'll be dealing with them in a like interchangeable manner. But you have to understand in the real documents that you will see, these terms are handled differently. In the real project documentation that you will be looking at in World Bank or ADB, these terms are handled slightly differently, right? But one big problem, again, I'm reiterating this part and we will see this today. No matter how complex you can make your mathematics in this particular topic, ultimately a lot of these values are coming out of people's perception. And there is no objective way for you to 100% estimate a probability of a particular event. For example, when you're talking about the cash flow happening, there's a 10% chance that cash flow will be 1.2 times the original predicted. There's no real or 100% accurate method for you to estimate this chance value. For most likely, people rely on past data. They most likely rely on somewhere else similar projects must have been done. But you are always, the world is changing every day. The mobile phone that you bought yesterday does not have the same performance today in terms of the economic conditions that we're talking about. Each company operates in a very different environment. They might have the same technology, but they might not be able to achieve the same cash flow using the same technology because they are operating. So there are two ways to judge it. One is you make it so complicated, nobody understands it, and therefore you are right. So that's basically you're confusing, and that's what happens. That's what happens in most of the thing. If you go to the depth, ultimately the values are coming from somebody assigned those values based on their experiences, their perceptions and things like that. But that value is so deeply embedded in the analysis that you are, as an individual decision maker, you have no chance to look at those numbers, and therefore you trust it, right? Most of the consulting jobs are around that. I'm not saying that consultants are bad. They do a lot of boring job, but they get a good money out of it. So that's the part. You outsource it to somebody who has some basic idea about or has some basic understanding of what they are doing, right? Other is that you try to involve people who are actually going to use your model as much as possible in the model building process itself, right? So instead of you assigning the value, maybe one better way is that you involve 10 people who have faced those problems in their day-to-day operations and involve them. But nobody has that much of time, and therefore the outsourcing model works, right? So And again, that is no guarantee, because ultimately it's a perception, ultimately it's an experience of individuals that you are trying to source. But how will you have a good estimation still is not clear. Should you interview 100 people? Should you interview 1,000 people in a 10,000 company, 10,000 people company? Nobody knows. Will you actually be getting it, right? So therefore, one neutral way to represent this information is, whenever you are dealing with your clients, make them understand that whatever the calculation you are doing is not an absolute truth. And there is always a chance associated with it. And chance, even if you assign a 0.2 probability, there is no guarantee that in the next event, or let's say if you toss a side coin, there is no guarantee that a coin will actually turn up head, right? It's ultimately a probability. It's not a reliability of the next outcome that will, you can never predict the individual outcome of the next event, right? So you have to sensitize the people. But in real world, people don't like this complications. They're like, give me a number, can I make a decision on it or not, right? So that's where the heavy lifting or the mathematics side of it gets you need to understand and then try to give the message more meaningfully, right? The other thing is, what you could do, the risk management part is, identify the sources which are contributing most to this risk and then try to do something about those sources, right? For example, you expect that in your particular project, the interest rate is a very sensitive variable. So then you need to perhaps buy an insurance to hedge your investment rate, that no matter what the outside market's interest rates are, at least for this project, I will be able to secure what rate I want, right? So the idea of risk analysis or the risk management is not to completely get rid of the risk. You cannot do that, but basically understand what factors are contributing to it and therefore hedge yourself against those factors. There are, of course, methods. Some are, you accept certain risk. In your day-to-day operations, you accept that, okay, this is typically you define a risk on severity versus their probability of occurrence, right? And you can divide this whole thing into 4 quadrants: highly probable and highly severe. Severe is basically the impact of an event on your business. So highly probable and highly severe risks, if there are, you definitely need to avoid them, and avoid them by design. Maybe you redesign your project such that this does not happen. For example, in Japan, a lot of earthquakes. So by default, every infrastructure that you make has to be earthquake resistant. You cannot expect, because it will immediately block your business and it is a high probability, right? Depending upon low probability and low severity, you can accept them. You can expect that, okay, on an average, I will have 10% extra budget in my day-to-day operation, so that if the risk occurs, I can still manage them, right? There could be high probability, low severity, and highly severe and low probability. These kind of risks, maybe you can outsource, you can insure or get insurance against that. So there are several different strategies. So risk management is still a valid field. It's just that these numbers have no guarantee that the next event, what will be the next event, you cannot predict that. Okay? Did I give you a politically correct answer? So I'm not saying that you should leave the field and not pursue a career in this. It's very important field. But a lot of the factors are difficult, and those are real risks, and those are difficult to quantify. A lot of the factors can also be quantified rigorously based on whatever the data is available, and therefore there is a mix of both. In terms of the probability, there are only 2 main concepts that I am going to need. One is something called an additive probability, and there's something called multiplicative probability. And give you an example without going into too much detail. So suppose there is a machine which can classify, or the output of a machine is a quality control measure. So a machine is producing some sort of an output, and this output can be classified into category superior, passing, and the failing. Category A, category B, category C. So a product coming out of a machine is either superior quality, just passes the quality criteria, or it's the failing the quality criteria, right? The items in each class from an output of 1000 items are 214 in A. You did an experiment for 1000 samples. You got about 214 items which were of category A, 692 were in category B, and 94 in category C, right? If the run from which this sample was taken is considered typical, by typical I mean that this this 1000 items, you expect that this is the generic behavior of this particular experiment. Typical is not the English, but the technical term here. What is the probability that machine will turn out each grade of product? And then the second part, this is the question number 1, and the second part is what is the probability of making at least a passable grade, right? So what is the probability of A? Right? The outcomes of A were upon total outcomes are 1000, A are 214. Similarly, probability of B and probability of C you can estimate 0.094 and 0.692, right? Total probability adds to 1, you can see here. And at least a passable grade, so it means at least B or A, right? C is not passing grade. So what is the probability of having at least A or B is you simply add the probability of B and A, because these events are kind of independent, right? That word is very important. It's a technical term, again, I know a lot of you know, but here you can simply add the probability of getting B and probability of getting A. So the at least passing will be somewhere about 692 plus 214 divided by 1000, or alternatively 1 minus probability of getting C, which is 1 minus 0.094. Okay, got the idea of these are basically independent events, and therefore the probabilities are more or less additive. Again, this is not a generic statement. I am just trying to simplify things for you. This is not a probability class, but just the basic concept that you will be needing in this particular course, right? This is another example of multiplication of probability, and I also want to introduce to you how the kind of common representation that you will face in this particular course also, right? So here, each of these circles are something called a node, okay? You will see the cash flow diagrams also possible to be represented in this kind of a diagram, which looks like a node arrow diagram, you can call it. I don't know what the technical term is, but essentially it describes you the information that there is a 0.1 chance that the interest rate in your calculation will be 12%, okay? There is a 0.7 chance that your interest rate used for calculation would be 10%, and there is a 0.2 chance that your interest rate will be 7%, okay? Now, in this case this is true, but it can also be different. At the other hand, there is a 0.05 chance that the annual saving will be $5,000. There is a 85% chance that annual saving will be $8,000. There is a 10% chance that annual saving would be $10,000, right? Here this is exactly same, but not necessarily. It could also be different, because when the interest rates are changing, your saving rate could also differ, right? Ideally, if interest rate is representative of the cost of capital for you, so the cost of capital will definitely govern how much money you are able to save on a particular trade, right? So these could be related also. These two, the kind of phenomena that I am describing, the interest rate and the annual savings, could also be related, conditional, in a way that given that there is a 0.7 chance of 10% interest rate, or if the interest rate is 10%, your savings have this probability distribution, compared to when your interest rate at 12%, your savings have this probability distribution. This could be different. For simplicity, I have taken it same here, right? Now, what is the probability that your interest rate is 10% and your annual savings are $8,000? I'm making two statements parallelly. I'm combining. I am asking you what is the probability that interest rates are 10% and an annual saving of $8,000. So what is the probability of interest rate 10% and what is the probability of annual saving of $8,000 is 0.85. So both of them combined happening, both the conditions simultaneously happening, is a multiplicative probability, right? It's not an additive probability here. So you get a chance of about 60% chance that both these conditions will be simultaneously satisfied. Get an idea of how the additive and the multiplicative probability work? Of course, very simple. I think I remember in my JEE days, this simple concept was spanned over a month time. So it's there, but I think this is how it is. Okay. The probability of interest rate 7% and annual savings of $10,000 is 0.2 and this particular branch. So what I am doing is I am basically selecting the nodes. Out of first decision is this node. So in this I selected this node. Then the second decision is about this node. So I selected this node. So essentially I end up selecting this particular branch. Making sense? Right? So you can actually estimate the coefficient probability of each of these branches also. For example, this will be what? 0.1 into 0.05. This will be 0.1 into 0.85. This will be 0.1 into 0.1 and so on and so forth. The total of all these values will come out to be 1. Okay? Alright. And again, reiterating, this does not have to be the same probability distribution. It could also be conditional that if your interest rate is 12%, the probability distribution of 5,000 is, let's say, 0.1, this is 0.8 and this is 0.1. This could also be the case. This does not have to be exactly replicable for same. Alright. So with that, we also, let me introduce a very important concept, or it's not very tough, but this is something we'll be using most of the time. There's something called a expected value. Expected value is nothing but essentially the average of what you expect given that you have a probability distribution given to you, right? Originally the average was a one single value. Now let's say you have 10% chance that the value would be, let's say, x. There is a 20% chance that the value will be 2x, and then there is a 50% chance that the value will be 3x. So what is the total? What is the on an average? What is the expected value for this variable? You can estimate. How? You take the probability score, multiply by the value, take the sum. Get it? So for example, it's basically a simply weighted averages, and weighted is coming by the probability of that particular outcome occurring. For example, if in this previous case, the expected value of the interest rate, on an average you can expect an interest rate of 12% multiplied by 0.1, 10% multiplied by 0.7 plus 7% multiplied by 0.2. What is this number? $3.33. How can it be so low? 1.2 plus 7. Okay, yeah. 9.4% is the average return that you could expect from this particular interest rate given this distribution. Similarly, average expected value of savings would be 5,000 multiplied by the probability of 0.05, 8,000 multiplied by 0.85, and then 10,000 multiplied by 0.1, and you simply add them to get the 8050. Make sense? This is how you calculate the expected value, and this is a generic formula for any variable. If you want to estimate, you estimate the probability. In this cases, in simple cases in a classroom, this will be given to you, and you multiply the xi with the probability of occurring xi, and you take sum of all the xi's for a particular variable. Alright, so let's look at an example. Let's say the present investment is 6,000 rupees, the discount rate is 10%. The year 1 cash flow probabilities are given. There is a 25% chance that in year 1 the cash flow would be 1,500 rupees. There is a 50% chance that the cash flow in year 1 would be 3,000 rupees, and there is a 25% chance that the cash flow in year 1 would be 4,000 rupees. Similarly, for year 2 and year 3 cash flows, the probabilities are also given. Here, there is about 25% chance that the cash flow would be 1,500 rupees. There is a 25% chance that the cash flow would be 3,000 rupees, and there is a 50% chance that there will be 4,000 rupees cash flow in year 3. Okay. So, this is how your cash flow series is going to look like. The average cash flow series or the expected value of the cash flow series is going to look like this. In your year 1, the expected value of the cash flow is what? 1500 into 0.25 plus 3000 into 0.5 plus 4000 into 0.25. Can you check if this is coming to be true? Then similarly, the cash flow average or expected value of the cash flow at year 2 is 1500 multiplied by 0.5, 3000 multiplied by 0.25, 4000 multiplied by 0.25 and the addition of that, right? So using this value, now if I ask you to calculate the NPV of this cash flow series, how will you calculate? Basically, once you have taken this probability distribution into account and you have calculated the expected values of each cash flow, then you are basically dealing with a normal cash flow series. You have an expected value and then you can simply discount it with respect to the formulas that we have seen already. So essentially that's what has been done here. This is nothing but the expected value of cash flow at year 1, which I already told you, divided by the discount rate, the factor of discount rate, similarly here and similarly here. So this is the expected value of this expected equivalent or the expected present worth of this cash flow series, given the probability distribution of individual cash flows. Okay, so this is how you actually account into the probabilities of, so for your projects also, each of these cash flows, you could make an analysis which is so complicated that you are able to estimate the probability distributions of each of these cash flows somehow using some information. And then if you have to do the present worth analysis, you convert individual of these cash flows into their expected value, and that cash flow series will give you an expected value of the present worth as well. Okay, got it? All right, let's look at a little bit more complicated example, and I'll solve this example with 2 methods. Both of them will give exact result, but let me give you the example. So the first cash flow is 200,000 rupees. Then there is a 30% chance that the cash flow in year 1 would be 80,000 rupees. There is a 40% chance that the cash flow in year 1 would be 110,000 rupees. And there is a 30% chance that the cash flow in year 1 would be 150,000 rupees. Then for this node, there is a 20% chance that the cash flow in year 2 is 40,000 rupees. Now, how to read that? Given that year 1 cash flow is 80,000 rupees, there is a 20% chance that the cash flow in year 2 would be 40,000 rupees. Slightly longer sentence, but that's how you actually represent it. Given that in year 1 the cash flow was 80,000 rupees, there is a 60% chance that the cash flow in second year would be 100,000 rupees. And so on and so forth. So here you see this distribution is different for each of the original, depending upon the year 1's cash flow, the probability distribution of year 2 cash flow also changes, and that is likely to happen because they could be representing the similar market condition. If on year 1 you are not able to do very good, you may expect not doing so good in year 2, or vice versa. It could happen otherwise. I'm just giving examples. Okay, so if the question is to estimate the expected value of the present worth of this entire probability distribution that I have given, there are 2 methods. One is you crash your, this is actually called crashing. You actually crash your analysis on each of these nodes. For example, for this node, what is the expected value of cash flow at year 2? You can estimate by just averaging these out. Right? Now, you know this value, you know the expected value of this value, and you can estimate the cash flow series using the same method that we just saw. Or you could go branch by branch, and I'll show you both the methods. Okay. First method, if you want to calculate the NPV, the first value is okay. There's no probability distribution. It's an initial cost without any probability. First look at this term. 0.2 into 40,000, 0.2 into 40,000, 100,000 into 6 and 150,000 into 0.2. Right? And this will be discounted by 2 periods. So 1.12, 12% is your, so it will be discounted by 2 periods. So this is you have converted all these series into an expected expected cash flow of year 2 for this particular node, right? Now, this node also has a probability of only 0.3. So, this 0.3 comes here. This is what? 80,000. There is a 0.3 chance that the cash flow in the year 1 would be 80,000, and you have already summed up this particular network already on this. So, this becomes the target. 80,000 upon 1.12, this particular cash flow is upon 1.12 square, multiply the whole term multiplied by the probability of occurring that particular node, right? So, you are essentially crashing this network onto each node, and then you are subsequently moving forward. In the second case, I am calculating this expected value of this cash flow first. This will be what? 130 into 0.3 plus 150 into 0.4 plus 160 into 0.3. This will be discounted for 2 years, so that will be like 1.12 square plus the cash flow here is what? 110 divided by 1.12. The whole network, this term added here will be multiplied by what? 0.4. Understood? 0.4, all the terms, individual nodes are being crashed, and that is how you do the analysis. Making sense? Do I need to explain it again? Essentially, you are crashing. This is basically called a tree diagram. You are crashing the nodes of tree in a sequential manner, right? So, this final outcome will be 190,036 rupees is your expected value of this cash flow, expected present worth of this cash flow series. Okay? There is another method, and another method is related to the joint probability method, which we also described as multiplicative probability. So, both of these are conditional statement. So, in year 2, the same statement that I have made, given that in year 1 the cash flow is 80,000 and there is a probability of it is 0.3, year 2 cash flow there is a 20% chance that it will be 40,000, right? So, each branch of the tree have a probability distribution, which is what? In this particular case it will be 0.3 multiplied by, that is 0.06. Now, this whole branch serves as a cash flow series for you, which is minus 200 plus 80 and plus 40. The present worth of this branch is what? 80 upon 1.12 plus 40 upon 1.12 square and minus 200. I am skipping the extra zeros, so be mindful. The whole thing will be multiplied by 0.06. Got an idea? How did we do the calculation? So, this is the present worth of this particular branch, which is, this is here, minus 200,000 plus 80,000 upon 1.12 plus 40,000 upon 1.12 whole square. The whole probability of this branch occurring is 0.3 into 0.2, which is 0.06, right? So, you can make a table like this where you are writing the probability of individual of these branches and you are writing the corresponding present worth of each of those branches. Then, if you have to estimate the expected present worth of the whole series, what you simply do is multiply the PW with the corresponding probability, which was 0.06. So, you get this value. Similarly, you keep on multiplying both the column A and B, and the final expected value of this whole series would be just the sum of the weighted multiplications that you have got. Concept remains the same. In one, you first crash the tree and you found an basically you going subsequently. In this, you are first estimating the probability of a particular branch, the present worth of a corresponding branch, and now you can apply the formula of xi into pxi and take a summation of that. Any doubts here, or is it not clear? The result that you will get from both the answers will be exactly same. This method I would prefer because for more complicated calculations, this is easier to visualize and this is easier to automate also for many softwares. This one becomes a little bit tricky, but as long as you are clear of what of you are doing, doesn't make a difference. But I think most of the softwares would probably work on this because this is a rather straightforward algorithm to implement. Right? All right. So this is expected value of anything given that probability distribution of, and then you have estimated expected present worth, expected annual worth, expected future worth. This could be a measurement for you to decide whether a particular project is interesting for you or not interesting. Right? This is how you assimilate the probability information into the analysis that we have done. Once you have obtained the expected value of the present worth, then everything that we have learned so far makes sense. You can make a judgment whether it is an investment for you or not. If you're comparing multiple alternatives, then also you can do using the expected values. All right. But then now that we have introduced probability, of course, things get a little bit more tricky and a little bit more interesting. And this is that in general, it's not only about probability is not only a measure of the expected, but also how likely it is going to vary from the mean value. Right? In every probability and statistics, there is a mean and there is a variance, right? There could be two series which means are equal, but then their variations are so big that you can't actually rely on what actually is happening, because individual of these terms are varying so much. Still the mean is same, but the dispersion is too much in a particular investment, right? So that also can become an important criteria for you to choose whether it makes sense for you to invest in a particular project. So let me give you an example. Let's say you have a proposal A and proposal B. And the probability of the scenarios of low demand, average demand and high demand is given to you 0.2, 0.6, 0.2, and correspondingly for each of these scenarios you are getting the present worth given here in this table is given. So the expected value of the demand, not present worth, basically demand is given. So expected value of demand in proposal A is what? 1000, 900 into 0.2 plus 1000 into 0.6 plus 1100 into 0.2, which is 1000, right? Expected value of demand in proposal B is also 1000, 400 into 0.2, 1000 into oh, I did a mistake, is it? This should be 0.2 and this should be 0.6. 1600 into 0.2 and 1000 into 0.6, and you will estimate this value is also coming out to be 1000. So both these cases have the same means, but you can clearly see proposal B has a much lower value for low case and a much higher value for high case. So again, this is not a bad thing necessarily. For some people, this is an opportunity that there is a chance that I will get much higher money. For some people, it is a risk that the variation is just too much. I cannot have a good value that I can rely on, and therefore this whole proposal is not good for me. Again, as an investor, you need to decide whether you like the variation or you don't like the variation. There is no absolute about the variation is good or bad. It's on you whether you like to play with the variation or whether you don't like to play with variation. But in general, you are going to have more confidence on proposal A, because the values are still staying close enough. You can expect that whatever the value, it will still be much more closer to 1000 compared to the proposal B, where the value could be anywhere between 400 to 1600 and you will be stuck with it, right? So confidence wise, proposal A gives more idea. Which one is acceptable depends on you. All right. So how do you measure the variations also? This is quite an important measurement that you need to do. So variance we defined as the value of xi minus the expected value of x, the whole square, multiplied by the probability of it. This is a very standard definition of the term variance, and then the under root of this expression is called the standard deviation, which you are most likely to use. So for any distribution to define, usually you give a mu, which is the mean, and then you give a value of standard deviation. That helps you understand how spread out or what is the distribution of this particular series, and that helps you make the decision. I'm not explaining this, but again, please go through that write-up that I have sent. If you're not able to understand the basic definition, let me know. But essentially, you need to the original xi value minus the expected value to the square multiplied by the probability, and then you take the sum of that series. So, in the proposal A, if you want to estimate the variance, there was a 0.2 probability of demand being 900. 900 minus the expected value we have already calculated, it is 1000 whole square plus 0.6 into 1000 minus 1000, which is the xi, of course 1000, and the expected value is also 1000, and then there is a 0.2 chance that the demand would be 1100 minus the expected value of the demand in proposal A, and you give, and the variance that you will give in this or get in this case is 4000. Okay. In the second case, 0.2 again by demand in case which is the worst case in this or the low demand cases, 400 minus 1000 square, 0.6 into 1000 minus 1000, and 0.2 into 1600 minus 1000 square. So the variance here you give is 140,000. And so while intuitively it makes sense that 400 and 1600 are too far apart, this is a formal definition of variance, and by this number you can quantify how spread out a particular series is, right? So more variance in proposal B. All right. Then problem with variance also, while it is a good method, it is not easy enough or intuitive enough to understand. And I'll give you an example of proposal A, B, C here. You see, in proposal C here, A and B are the same that we have seen. In proposal C, the values are almost multiplied by 1000 times, right? So in this case, the variance is coming out to be this huge value, and the standard deviation is coming out to be this large number, even pretty large number, compared to the values that we have calculated here, 4000 and 144,000. This is the variance. This variance is 3-4 order higher, right? So how do you compare such proposals? Becomes the question. So comparing with standard deviation, which is just 63 and 379, would be misleading, because immediately you would see this particular project C has a huge variation, and therefore you might be not inclined to accept that. So in that case, what you do is you normalize the standard deviation, and this is called standard deviation divided by the expected value, which is the sigma by mu. This is called coefficient of variance. This is a more normalized value to represent, and therefore you can compare these numbers easily. Okay. So in this case, let's just calculate that. So 63 divided by mean is what? 1000. In this case, this is for A. For B, it is 379 divided by 1000, and for C, it is what? The standard deviation is 12,649 divided by, can you give me the number? What is the expected value of proposal C? Is it 10 lakh? 10 lakh is the expected value, and then this is coming out to be what? 0.012. So see, the normalized numbers are still on comparable range compared to 12,649, 63 and 379. So this is more a normalized value. And of course, you could argue that why only we are normalizing with respect to the expected value, why are we not normalizing with respect to median value, mode value? Statistics is full of variations. You can expect whatever is giving your good answer or acceptable answer that you are liking, you can always use those measures, but this is a standard definition of this. Okay. So this is where we'll stop. I'll show you how to use this information to make decisions in the next class.